Mr. Causey here. In this video we're going to concentrate on the idea of the argument of a complex number. For instance, suppose we've got negative 2 minus 2i as plotted in the diagram. It has a modulus of 2 root 2. Now its argument, remember arguments are measured from the positive real axis in a anti-clockwise direction with a positive rotation, in a clockwise direction would have a negative rotation. So suppose we go in a anti-clockwise direction. In this case we get an argument of 5 pi upon 4. We could also rotate in a negative direction, in a clockwise direction, to get an argument of negative 3 pi upon 4. Now suppose we're at the 5 pi upon 4 argument, and we could choose to add 2 pi to that. That's another 8 pi upon 4 added on, or we could be at the negative 3 pi upon 4 for the argument and go in a clockwise negative rotation direction by 2 pi to get another argument. So adding 2 pi to one argument will produce another argument, or a similar way if we subtract 2 pi from one argument we'll get another argument. So adding or subtracting multiples of 2 pi. It's adding integral multiples of 2 pi will produce others. So there's an infinite number of arguments. Now we're going to select one of these as a representative. In this case it would be negative 3 pi upon 4. Now why choose that one? Well, this is what the rest of this video is going to explain. The symbol we use for this particular argument is capital ARG, arg of z, and it is special in that it lies in the range negative pi, not including negative pi, all the way up as a maximum to pi, and this time we're allowed to include pi. So if we have an argument in that range, then it's called the principal value of the argument. So let's once again have a look on the diagram at that. So not negative pi, but any argument that lies through the third and fourth quadrants up into 0, and then through the first and second quadrants up to a maximum of pi, and including the value of pi. So here's the definition. Principal argument of a non-zero complex number z, unique argument theta satisfying that inequation. And it's denoted by capital ARGZ, argz. Now to note, it's non-zero. 0 has no argument. Note the capital. We don't use small ARGZ. And there is only one argument in that range, since they all differ by multiples of 2 pi. So let's illustrate the idea of a principal value by picking a set of complex numbers. Now root 3 plus I has a principal argument of pi upon 6, and it lies in the first quadrant. Let's look at a related complex number, negative 3, root 3 plus I, and to get hold of its argument, let's not just stop off at the point, let's go right the way to pi, and we can see we would have to subtract pi upon 6 to get that argument. So the principal argument of this complex number is pi minus pi upon 6. Let's now move into the fourth quadrant. A related complex number would be root 3 minus I. And to get the argument of that, we would have to rotate in a negative direction by pi upon 6. And there we get the principal value of that complex number. Now the final related complex number lies in the third quadrant. It would be negative root 3 minus I. And how do we get the argument for this complex number? Well, we do the negative of what we did in the second quadrant. Let's go, instead of all the way around to pi, let's go in a negative direction for the rotation all the way around to negative pi, and then we add a positive rotation of pi upon 6. So our argument there is negative pi plus pi upon 6. That's the negative of the second quadrant argument, just as the first quadrant argument and the fourth quadrant argument are the negatives of each other. Now there's nothing particular about root 3 plus I. We could generalise that, and so long as a and b are positive, a plus bi in the first quadrant, there's the related complex numbers, and let's call phi the first quadrant angle. So again we can get these principal values in the same manner. So let's focus now on how we calculate the first quadrant angle phi. So there's a right angle triangle in there. It involves phi, it involves the imaginary part and the real part, b and a. Opposite over adjacent, that's the tangent. So the tan of phi is b over a. So we will discover phi by finding the angle whose tangent is b over a, tan to the minus 1 b over a. Now remember, a and b we said were positive, and that guarantees that that complex number was in the first quadrant. In the general case, we will not know whether the real and imaginary parts are positive or negative. So that's the first quadrant angle, tan to the minus 1b over a. So let's see if we can begin to develop a method of finding the principal value based on finding the first quadrant angle. Now there are exceptions. If the complex number lay on the axes, then that's a special case. We'll have a look in a minute at that. But as a step one, we'll assume we've got a complex number x plus I y. And as I said, if that lies on the axis, if it's a real number, its argument would be 0. If it's a purely imaginary number with a positive imaginary part, it would be pi upon 2. And if it's a purely imaginary number with a negative imaginary part, it would be negative pi upon 2. And if it was a negative real number, the argument would be pi, not negative pi. But these are special cases, and they'll be very obvious at the time. So if they're not on the axes, what we do is we find the first quadrant angle by assuming the same values, but take the absolute value. We rip off the negative sign. So y over x without negatives. So that's tan to the minus 1. Find the angle whose tangent is the imaginary part, made positive if you need to, divided by the real part, made positive if you need to. And that guarantees that we've found a first quadrant angle. And then step 2, how do we know where that complex number is? Well, let's just plot it and find out. It should be then obvious which of the quadrants we're in. And then we can use that first quadrant angle to find the principal argument. So if the complex number z happens to be in the first quadrant, then we've found the principal argument. It's just phi. If we're in the second quadrant, well, remember we rotated a positive direction all the way around to pi and then subtracted the first quadrant angle. The third quadrant was the reverse of that. we rotated in a negative direction all the way around to pi, so that's negative pi, and then added the first quadrant angle, and finally the fourth quadrant was just the negative of the first quadrant angle. So that's the whole system for finding principal arguments. So this all must seem fairly complicated. It's not really, and I think the way you can understand it properly is to do some actual examples. So I'm going to put some examples up. I'd recommend that you stop the video at this point and attempt these examples before we get into the details of the solutions. Well, okay, let's try the first set of examples. So part A. And here we're looking at the complex number z equals -1 plus root 3i. And we'll attempt to find that first of all on the diagram. So real part -1, imaginary part root 3. And it's in the second quadrant. So the first task is to find what the first quadrant angle is. And remember, that's given by the angle whose tan is the imaginary part, made positive if needed, and divided by the real part made positive, and that would be +1. So we're looking at the angle whose tangent is root 3. Now, diagram, if we take an equilateral triangle of side 2, chop it in half, we'll get a side 1, 2, and by Pythagoras root 3. Remember, angles in an equilateral triangle pi upon 3, and the tangent of pi upon 3 is root 3/1. So the first quadrant angle, pi upon 3. Now, where is z? Z's in the second quadrant. And remember, in the second quadrant, to get the principal value of the argument for z, we go all the way around to pi and then come back by the first quadrant angle. So it's pi minus pi upon 3. That'll be 2 lots of pi upon 3. We've got 3 lots of pi upon 3 minus 1 lot of pi upon 3, which gives us 2 lots of pi upon 3. So that's part A. So moving on to part B, that's the real number -4, and it's on the real axis 4 units from the origin. And we can just read off the principal value of the argument, and that would be pi radians, not negative pi radians. We include pi but not negative pi. So pi radians for that. Let's now move on to part C. That's 3i, purely imaginary number up the positive direction of the imaginary axis. A distance of 3. And again, we can read off the principal value of the argument of z in this case as pi upon 2. So finally, let's move on to part D. That's -3 minus 3i. So it has a real part, -3, and an imaginary part of -3. Now, let's have a look at the first quadrant angle. And remember, we get that as tan to the -1 of the imaginary part made positive if needs be. That's -3 changes to 3, divided by the real part made positive. That'll be +3. So we get tan to the -1 of 1. So what angle has a tangent of 1? Well, let's take a square of side 1 and chop it in half. Pi upon 4 is the required angle. Now where is Z? Well, Z's in the third quadrant, and to get the principal value of the argument in the third quadrant we go all the way back to negative pi, that's a negative rotation, and then add on the first quadrant angle, in this case pi upon 4. So it's minus 4 lots of pi upon 4 plus 1 lot of pi upon 4, which gives us negative 3 lots of pi upon 4. So let's move on now to example 2, the 4 examples in example 2. So let's tackle part A. That's negative 5i. That's down in the negative direction on the imaginary axis. And it's 5 units from the origin, so it has a modulus of 5. Principal argument is negative pi upon 2. So written in polar form, Z would be equal to, remember we start with the argument of Z, that's 5 in this case, times the cos plus I sine, so it's the cosine of negative pi upon 2 plus I sine negative pi upon 2. And that's part A. Now moving on to part B, we have 3 root 3 minus 3i, so the real part of that complex number is 3 root 3, and the imaginary part is negative 3. So we're down in the fourth quadrant. Now, calculating the modulus of that complex number, remember the formula for that's the square root of the real part squared plus the imaginary part squared. And the real part is 3 root 3, so we square that, plus the imaginary part is negative 3, and we square that. Now 3 times 3 is 9, root 3 times root 3 is 3, 9 times 3 is 27, plus negative 3 times negative 3 is 9, 27 plus 9 is 36, root 36 is 6, so we have a modulus of 6. Now the first step in finding the principal argument would be finding the first quadrant angle. And to do that we have phi, it's tan to the minus 1, and we look at the imaginary part, make it positive if need be, that's 3, and the real part 3 root 3. 3's cancel, we get tan to the minus 1 of 1 over root 3. So which angle has a tangent that's 1 over root 3? Let's examine a equilateral triangle of side 2, chop it in half, right angled triangle, side 1 and root 3 for that side. So pi upon 6, half of the pi upon 3. Pi upon 6 is the first quadrant angle, and since that complex number is in the fourth quadrant, the principal argument would just be the negative of the first quadrant angle. So arg Z is negative pi upon 6. So we're all ready for writing Z in polar form. So it's the modulus of Z, which is 6, times cos negative pi upon 6 plus I sine negative pi upon 6. So part C. Here we have a complex number negative root 3 minus I. Real part is negative root 3. Imaginary part is negative 1. So let's calculate its modulus. That's the square root of the real part squared, negative root 3 squared, plus the imaginary part squared, negative 1 squared. So that'll give us 3 plus 1 is root 4. So it's 2 for the modulus of that complex number. Now, first quadrant angle, phi, as we're calling it, tan to the minus 1, imaginary part made positive, that's just 1, and the real part made positive, that's root 3. So again, we've got what we had in the previous example, pi upon 6 for the first quadrant angle. Now it's in the third quadrant, and remember what we do to find the principal value of the argument in the third quadrant. We go all the way from the real axis in a clockwise or on a negative rotation by negative pi, all the way around to negative pi, then come back by the first quad angle. So that's negative pi plus the pi upon 6. So it's negative 6 lots of pi upon 6 plus 1 lot of pi upon 6 be negative 5 lots of pi upon 6. So polar form, so that's the modulus, which is 2 times the cosine of negative 5 pi upon 6 plus I times the sine of negative 5 pi upon 6. So the last example, part D, where we are examining negative 1 plus I. So the real part, that complex number is negative 1, and the imaginary part is 1. So it ends up in the second quadrant. So let's look at the modulus of this number. So the modulus of z is square root of the real part squared, negative 1 squared, plus the imaginary part squared, which is 1 squared. So there's 1 plus 1, that's square root of 2 for the modulus. And if we look at the first quadrant angle, we'll have tan to the minus 1 of the imaginary part, that's 1, divided by the real part, but we make it positive. So it's tan to the minus 1 of 1. What angle has a tangent that's 1? Well, that'll come from a square of side 1, chopped in half. And we can see that's pi upon 4. Tangent of pi upon 4 is 1 over 1. So first quadrant angle is pi upon 4. Now where is z? It's in the second quadrant. And remember, to get the principal value of the argument, the first quadrant, in the second quadrant we go all the way around to pi and then come back. So subtract the first quadrant angle. So arg z is pi minus pi upon 4. So that's 4 lots of pi upon 4 minus 1 lot of pi upon 4. That'll be 3 lots of pi upon 4. So we're now in a position to write down z in polar form. So the modulus is root 2 times cosine of 3 pi upon 4 plus I sine 3 pi upon 4. And that's our examples completed. So that's Mr. Corsi signing out, and hope you enjoyed the video.